Hey everybody! I wanted to do some of your problems from your practice. Okay, so this is your practice item 4, and if you read it here, it says the table represents the frequency of occurrences for numbers 2, 4, 6, 8, and 10 when Jade tossed a cube. Okay, Jade tossed a cube with faces numbered 2, 4, 6, 8, 10, and 12. The results are recorded in the table. What outcome value is the largest discrepancy between the experimental and the expected probability of this experiment? I'm gonna bring my webcam over. Sorry, I thought I was with you guys, but I wasn't. Okay, so you guys, if you look at this problem, this is weird to me, but this girl Jade, she's got a die that doesn't have any odd numbers. Okay, so she's got a number cube, and it's got the 2, it's got the 4, it's got the 6. Okay, and then it doesn't have the 1, 3, 5. It's got, instead of that, it's got like 8, 10, and 12. Okay, so that means the sample space would be all the possible rolls, which would be 2, 4, 6, 8, 10, 12. Okay? And what that means is that the theoretical probability of any number, of any of those numbers, 2, 4, 6, 8, 10, or 12, is 1 in 6. Okay, because there are still 6 possible rolls, just like a regular dice. She doesn't have any odd numbers. I don't know where she got this die. I don't love that they call this expected probability. This should say theoretical. Okay, theoretical is what we expect though, so there's a logic to it. Okay, so when they talk about the discrepancy, okay, what they mean here is the difference from what we should get. Which of course is just, it's the 1 over 6. Okay, let's go ahead and change that into a percentage here. So I can take any decimal and turn it into percent with division. 1 divided by 6 is getting me 1.6 repeating. I'm sorry, 0.16 repeating, like that. And if I want to round this, I would round to the hundredths place and say this is about 17%. Okay, now as far as which one has the biggest discrepancy, if you look at the table, there are 2 values here that stand out. Okay, the 6 and also the 8. Okay, those are the largest and the smallest frequencies in the table. The other thing we need to notice here is the total. The total's not given, so we need to figure it out. How many times did this girl Jede, Jede, well, this person, Jede, I don't know if Jede is male or female. The name doesn't tell me. 10, 9, 6, 15, 13, and 8. Okay, if I add these together, all of these frequencies, I'll get the total number of rolls. Okay, so let me take a look here. I'm gonna, let's see, 9 plus 6 is 15. You could just do this on a calculator. I probably should do it on a calculator because I might make a mistake. 8, 9, 10, 11. So 20 and 11 would be 31. Carry the 3. 3, 4, 5. No, 3, 4, 5, 6. 61 total rolls. Okay, and I'm just going to add those up in a calculator just to be sure, because this is a really long problem. I don't want to get it wrong because I misadded. 15 plus 13 plus 8. Ah, yay, I did it right. Yay, 61. Okay, so now what we can do here is we can actually find the relative frequencies. Okay, and remember those are the same as the expected, what did they call it? Experimental probability. So the probability of a 6 was, we got 6 of them out of 61 total. Okay, I'm going to go ahead and change that into a decimal and a percent. So 6 divided by 61 is that 0.983 and keeps going. So 0.098. I'm going to say that's approximately 0.10 or 10%. Okay, so if it's 10 and I was supposed to get 17, that's a pretty big discrepancy. Okay, but let's see if it's as big as the 8. So for the 8, I got 15 of them out of 61 total rolls. I'm going to divide to find that probability. 15 divided by 61. And I'm getting 0.245. 0.245, which I'm going to round up. If I round to the hundredths place, the 5 is going to round it up to 0.25 or 25%. Okay, so now which one is the bigger discrepancy? Okay, so I'm gonna say if this 17% is normal, you know, like which one is more abnormal, getting 10% or getting 25%? So what I'm gonna say here, if you think of the 17 as what's normal, the 10% is 7 percentage points lower than it should be. Okay, and then the 25 is 8 percentage points higher than it should be. How am I getting those? I'm subtracting, you guys. Okay, so 17 minus 10 is 7, and then 25 minus 17 is 8. Let me erase this little stray mark that I made here. Okay, so I'm finding the discrepancy by subtracting, and I'm saying that the 8 is a bigger discrepancy. It's further away from the percent that I was supposed to get. So this is the answer that I'm going to put here. It's the 8. Okay, and if you look here, it says what outcome value. Okay, those are the 2, 4, 6, 8, 10, 12. Okay, so the outcome value that was furthest away from the theoretical probability was 8, with a 25% occurrence in this this die rolling experiment here. Okay, I've got one more that I want to show you. So just a sec, and this one's a little quicker. So hang with me here. I'm just gonna snip it and then I can draw on it, but it's about light bulbs. I don't want you to get too excited. And you guys, this is actually really used in the real world. Okay. I know everybody's like on the edge of their seat, like, oh my gosh, it's about light bulbs. It's really used by real light bulb factories. What? Okay, Company X tested its light bulbs to see how long they would last. On a production line, 2,500 bulbs were taken and tested. That's our total. The department in charge reported that out of 2,500 bulbs, there were 2,200 bulbs that burnt out after more than 1,500 hours of use. Okay, Lucy purchased a light bulb from Company X. What is the likelihood that it will burn for more than 1,500 hours. You guys, you might have noticed that I did not highlight the 1,500. Okay, that's because that's not a number we actually need to do math with. Okay, 1,005 plus hours is what we're defining as a good bulb. Okay, that's just how long it lasts, and they say, yeah, we're good there. If it lasts less than that, you're like, oh, I just bought this. How did it burn out already? Okay, so we don't actually need that number. All we need here is to look at the good bulbs over the total. And think about it. You guys, that's the experimental probability. That's the relative frequency. All this stuff is coming together in this example of a real world thing that people actually do. Okay, the number of good bulbs over the total. That's 2,200 over 2,500. Okay, and you can just divide that in a calculator. And then here's a trick for simplifying fractions. If you divide by 10, it takes off a 0. So see, I just divided by 10. I'm going to do it again. And then in my calculator, I'm just going to do 22 divided by 25. Okay, and I did that earlier today. You can check me, but it is 0.88. So look here, it says answer in decimal form. So I'm done. That's all they wanted me to do in this problem. Okay, but what I want you to realize is that Lucy has an 88% chance of buying a good bulb. And that's a 1,500 plus hour bulb. All right.